Hi there. There's a few things that we need to go over. First is the rule of 4 for functions. This says that there are 4 unique ways that a function can be represented. They are real-world examples, data tables or ordered pairs, symbolically, and through graphs. The link below has an example of each for each of the 9 function families. I recommend you pause the video and open the link in a new tab so you can follow along when I get to function vocabulary that refers to the graphs. Our first function vocabulary word is relation. A relation is any relationship between one set of things and another, so that each thing in the first set, the domain, the input, the independent variable, or the x value, is paired with at least one thing from the second set. Our dependent variable, our output, our range, or our y value. Remember, we want Dix and Roy, not rocks and die. It could look something like this. You see in this example that A goes to 17 and 5, D goes to 12, and C is paired with 4. A goes to 2 different outputs, but each input is still used at least once, which is what is required of it for it to be a relation. Now, for a relation to be a function, each member of the domain must be paired with only one member of the range. So for this example, we could make it a function by either erasing the connection between A and 17 or between A and 5. Let's do 17. Now, everything in the domain is used exactly once and not paired with more than one thing from the range. So now our relation is a function. Now let's look at function notation. We're used to writing our functions, our equations, in terms of y equals something with an x, like y equals 3x plus 5. With function notation, there are 3 common ways we could write the same expression. They are f of x equals 3x plus 5, g of x equals 3x plus 5, or h of x equals 3x plus 5. They can all be used interchangeably, but f of x up here is the most common one. They all mean the same thing as our initial equation, y equals 3x plus 5. Next, we're going to talk about continuous functions. Simply, a continuous function is a function whose graph has no breaks or holes. That means it can be drawn without having to lift your pencil off the page. Now is where the link might help you some. Almost all of the example graphs are continuous, but if you look at the graph for the rational expression, second from the bottom on the first page, you'll see that it has 2 parts to it that are not connected. It would be impossible to draw this graph without lifting your pencil. This means that this graph is not continuous. But if you look at the other graphs, you'll notice that even though not all of them are smooth, they all can be drawn without lifting your pencil, which means that all of the other graphs do represent continuous functions. Next, we have discrete functions. A discrete function is not continuous. It will have a finite number of inputs and outputs. For example, the number of times you dip a bubble wand into the jar of bubbles, if that were a function of how many bubbles you blow, this would be a discrete function because you cannot have a continuous graph of this data. You cannot have a half dip or a half bubble. Either you dipped the wand or you didn't. Either you get bubbles or you don't. Next, we're going to talk about inverse functions. An inverse function is the undo operation. If we look at the example from earlier of y equals 3x plus 5, we can find the inverse by switching the x and y so it becomes x equals 3y plus 5 and solving for y again. We will get y equals x minus 5 over 3, like so. If you get out a pencil and some scratch paper, you can pause the video and see how this works. When you make a data table for your original equation and put your output values from that as your input values for the inverse equation, you'll get back your original outputs. I'll wait while you try it. Here are my data tables. See how I took my output values from the original and used them as my input values for the inverse? When I did that, the output values from the inverse function matched perfectly with the inputs I first used. Isn't that amazing? Reminder, a function is a relation in which each output goes to only one input. A one-to-one function is a function with only one output for each input. So here's a bonus tip for you. One way to see if a relation is a function is to look at its graph. If a vertical line can be drawn anywhere on the graph and only cross it at one point, then the graph is a function. This is called the vertical line test. A similar method is used to tell if a function is one-to-one. Looking at the graph, if a horizontal line can be drawn anywhere and only cross the graph once, then it is one-to-one. This is called the horizontal line test. Look at these graphs and see if you can tell which ones are functions and which ones are one-to-one and which are both. Pause the video if you need some time to look at them. A and C are functions. Nowhere can I draw a vertical line on these graphs and have it cross the graph at more than one point. B and C are one-to-one because nowhere can I draw a horizontal line that will cross the graph more than once. Based on this, C is the only graph that is a one-to-one function that is shown in this example. Look at the graphs from the link and see which of those are one-to-one. Pause the video and take your time. Next, I'm going to talk about piecewise defined functions. These are functions whose graph are made using two or more formulas. For example, we could have this. F of x equals x squared if x is less than 0, and f of x equals negative 3x when x is greater than or equal to 0. A piecewise function does not have to be continuous like this. If we used f of x equals negative 3x plus 5 when x is greater than or equal to 0, it would still be piecewise, although it would no longer be continuous. A stepwise defined function is a piecewise constant function, which is a function of the form y equals some constant. These will often look something like this. It's kind of like a staircase. The most common way to get this is to use a rounding function in which you round your outputs either up or down to the nearest whole number. We just have 3 more things to go. For these, it will be useful to have the link open and be looking at the graphs. First, go back to the rational graph. The reason why it won't be continuous is because it has a vertical asymptote. An asymptote is a line that the graph will approach but never touch. The rational graph also has a horizontal asymptote. Besides these two, there is one more type of asymptote, the oblique asymptote. This asymptote is one that is diagonal. Look at the other graphs and see which ones have asymptotes and see if you can identify whether they're horizontal asymptotes or vertical asymptotes. Now I want you to look at the quadratic graph. This graph is concave up. That means that its curves such as its endpoints are up. Another way to think of it is that it will catch rain. Parabolas, the quadratic graphs, can also be concave down, so that their endpoints are going down. If it is concave down, you can think of it as protecting you from the rain. Look at the cubic graph. It is both concave up and concave down, but in different places. Can you tell which is which? Remember, when it rains in graphland, the puddles gather where it's concave up and the water rolls off where it's concave down. In other words, rain builds up where it's concave up and keeps going down when it's concave down. The important feature that allows the cubic graph to be both concave up and concave down in separate places is an inflection point. An inflection point is a point where a graph changes concavity. Since the cubic example graph only changes concavity once, that means it only has one inflection point. How many inflection points does this graph have? 3, because it changes concavity 3 times. It goes from down to up, that's 1, from up to down, that's 2, and from down back to up again, that's 3. Go back and look at it some more if you need to. Now what about this graph? This graph only has 2. Goes from up to down, and then from down back to up. A quick thing to note is that if the ends of the graph are pointed in opposite directions, there will be an odd number of inflection points. And if the ends are going the same direction, there will be an even number of inflection points. Now, look at the quadratic and absolute value graphs. These two have a change in direction going from increasing to decreasing, or vice versa, but not a change in concavity. This change in direction is called a turn. Look at this graph again. How many turns does it have? Increasing to decreasing, that's 1. Back to increasing makes 2. Decreasing again makes 3. And back to increasing one final time, we have 4 turns. See which other families have turns. Bonus! A dynagraph is a tool that is used to represent functions dynamically. I do not have an example of this ready, but you can Google it and find one. They're kind of fun to play with. One thing that I already assume that you know is an ordered pair is a combination of two numbers, which means the order of the numbers matters, in which the first coordinate is the x-coordinate and the second is the y-coordinate. Most of the data on the link is in this form. The identity function, I'm also assuming you know, is the do-nothing function. You put in a value and it gives you back the same value every time, such as f of x equals x or y equals x. I hope you have found this helpful. Have a great day.